in chemistry, there's a skill that you need to have that is not utilized all that often, but when you do use it, it's extremely important. That is interpreting simple graphs. So we're going to cover two. We're going to talk about heating and cooling curves, and we're going to talk about phase diagrams. So let's talk about the heating and cooling curve first. So let me just change my color real fast so you guys can see. Okay, now this is what's called a heating curve. Now you'll notice it's a heating curve because the temperature rises as the process goes on. So heat is being applied to a substance, and as that heat is being applied, it's undergoing certain changes. We're going to talk about those changes with respect to not only what phase it's in, but also what's happening to the intermolecular forces. So what's going on the molecular level. And that's the big difference in graphs in math class versus graphs in science class, is graphs in science class are physical representation of data of something that's going on chemically or physically to the substance. So down here at point A, so you're going to need to make this graph on your paper. So copy this real fast in so that you can diagram out what I'm going to diagram as well. So at point A, we are all solid. Nothing has happened to the substance so far, and now we're going to begin to heat it. So as we move from A to B, we are heating our solid. Nothing fancy. Molecules are gaining energy, all those kinds of normal stuff that we'd expect to go on with heating of a solid. Now, point B is an important point. At point B, we have hit our melting point. So this is the first point in which our solid is turning into liquid. So we have no liquid prior to point B. Extremely important. So no liquid before point B. As we move from B to C, our solid is changing into liquid. And I'm just going to use a little script L because a regular L will look like a 1, and I don't want you to get confused. So as I'm changing from B to C, our solid is turning into a liquid. Now that's what's happening as a phase, but what's happening on the molecular level? Here, the reason it changes from solid to liquid is our IMFs, our intermolecular forces, are being weakened. The only thing that separates a solid from a liquid from a gas is the strength of the intermolecular forces, how tightly packed those molecules are. Solids have extremely firmly packed molecules, nice crystalline structures, but liquids do not. Liquids are free-flowing. They've got no definite shape. So that's because those intermolecular forces have allowed the molecules to spread out, and now they're beginning to weaken. When I hit point C, now this is going to sound a little weird because I'm a heating curve, but point C is actually my freezing point. So if this was a cooling curve and I started at F and I worked my way down, then C would be considered my freezing point, which would be the first point that solid appeared in this process. Okay, so this could also be called my freezing point. As I move from C to D, I am simply all liquid, so I am heating my liquid all the way up to D. Nothing is changing about the molecules. Nothing is happening. All the molecules are doing is they're getting a little bit more energy. They're starting to vibrate more. Bam. Now we get up to point D. And like point B, this is where a new phase is possible. So at point D, I have my boiling point. So point D is the first place that I could see gas. No gas is present before point D. As I move from D to E, my liquid is changing into a gas. Now, before, when I changed phase, something had to happen to my intermolecular forces, and the same kind of thing is going to happen here. As I change from liquid to gas, my intermolecular forces are going to be broken. Okay? No intermolecular forces, because remember, gases have no attractive or repulsive forces. They are moving randomly at all times. So as I move from liquid to gas, now you'll also notice that the distance from point D to point E is greater than the distance from point B to point C. That's important. Why? Well, think about it. Intermolecular forces from B to C are only being weakened. But from D to E, they're actually being physically broken. There are no more. So the energy required to break an intermolecular force here is going to be much greater than the energy required to weaken the intermolecular force down in B and C. That's why the distance is so long. FYI, that could very easily be an SAT-2 question, a test question, an AP question down the road, something like that. They like to do questions like that about their graphs. So D to E is longer because it takes more energy to break forces than it does to weaken. Once I hit point E, like point C, would be for the reverse process, but this would be my condensation point. Gas changing into liquid. And from E to F, I am all gas. So from E to F, I am heating my gas. And at point F, like point A, I am all gas. Nothing additional is happening to the molecules. All they're doing is being more energetic and bouncing around a whole lot more, but they're always gas. Okay, so that covers heating curves. And like I said, a cooling curve would just be the opposite. It would start from point F and it would be over here, and it would go zigzaggy down until it got to all solid down below. Now let's talk about phase diagrams. Okay, so pause the video, copy this phase diagram into your notes. Now, a phase diagram is a graph that demonstrates the pressure and temperature at which a substance will exist as either a solid, a liquid, or a gas. Now, the solid, liquid, or gas always appears, the section for solid, liquid, or gas always appears in the same spot regardless of how the phase diagram looks. Sometimes you'll see phase diagrams that kind of like, they look like this. They have this really tiny section because there might only be a little bit of liquid for that substance, or a really large gas section if it's always a gas. It doesn't matter how big these sections are because it will always be solid on the left, liquid in the middle, and gas on the right, on the bottom right. So now there are 6 phase change processes that occur in these phase diagrams. Before I identify A, B, C, and D, let's talk about those first. Let's do the easy ones. If I start as a solid and I move to become a liquid, think about it. Solid changing into liquid is melting. And you'll need to know these 6 phase changes because they pop up often on standardized tests. From liquid to solid, easy, freezing. From liquid to gas, we know is boiling. From gas to liquid is condensation. Now, there are alternative words to these too. You know, some people like to use vaporization as they're moving from liquid to gas, which is possible also if it's not actually boiling. Vaporization is fine too. Any words that mean that phase change are interchangeable in all of this. Now let's get to the 2 hard ones. Solid into gas directly. Now notice that this solid changing into gas does not pass through the liquid phase. Very important. So as if I change from a solid to a gas without passing through the liquid, that is called sublimation. Dry ice is your best example of that. Solid CO2. Dry ice is a solid substance turning directly into gas without passing through the vapor phase. As an aside, that's the reason they use dry ice when they package ice cream. Ice cream is packaged in cardboard cartons, and if they were to use ice, as the ice melted, as the ice cream is transferred from its wherever it's made to its destination, from Turkey Hill's farm, Turkey Hill to wherever, as the ice melted, it would create water, and that water would make the cardboard soggy, which make all the ice cream melt and just get mushy. But if they package it in dry ice, when the dry ice disappeared, it turns into gas and it pours out the sides. And sometimes you might have actually seen this. If you've been driving down the highway behind a truck and a whole bunch of what looks like steam is coming out of the back of the truck, it's probably got dry ice in it, and that is not steam you're seeing. It's actually the cold vapors of the dry ice coming out of the car and condensing the water vapor that's in the air around the truck. So, just an aside. Now, if I go from gas into solid directly without passing through the liquid phase again, that is called deposition. Okay? Interesting enough is actually the process they use in champagne. Believe it or not, if you've ever looked at a bottle of champagne, there are no bubbles. If you shake a bottle of soda, you'll see bubbles. even if it hasn't been opened yet. If you shake a bottle of champagne, you don't see anything. And it's weird like that. But there is carbon dioxide in that champagne. What actually happens is when you release the cork on a champagne, it actually causes such a drastic pressure change in the carbon dioxide that's dissolved in the liquid that the dry ice actually jumps from being a gas, because it's done at a specific temperature. It jumps from being a gas into being a solid and forms very tiny dry ice crystals. Those dry ice crystals then immediately sublimate and turn back into gas, and that's what makes champagne bubbly. See? Chemistry is awesome. So anyway, so now those are my 6 phase changes. So make sure you be able to can identify all 6 changes that are going on. Now let's talk about other things. Other important items that are on green on green is probably not a good idea. Let's talk about other points along this curve. Point C is what is called the triple point. The triple point is the point at which, is the pressure and temperature at which all 3 phases of matter exist. I'll repeat that again. It's the pressure and temperature at which all 3 phases of matter exist. Point D is what is called the critical point. I need to spell critical right. The critical point is the highest temperature at which the substance can exist as a liquid. Okay, the critical point is the highest temperature at which the substance can exist as a liquid. Any temperature above that, it's automatically a gas. Okay? Now, if your point occurs on a line at exactly 1 atmosphere, that is what is called normal. So, if I said to you the normal boiling point, what I'm actually telling you is the boiling point at 1 atmosphere. Okay, so that point can only occur when it's at 1 atmosphere. If I was down here, let's pick the boiling line. If I was down here on my point, could this be boiling? Absolutely. Can it be the normal boiling point? No, because I am not at 1 atmosphere. Okay, so that's really important. Now, points like B, A, D, C, etc. Any point on a line represents the equilibrium between 2 or more phases of matter. Okay, C would be the only point where you could have 3, but any other point is going to be 2 or more phases of matter. So for example, point B down here represents the equilibrium between solid and gas. Now, what does equilibrium mean? Equilibrium does not mean the same amount. Equilibrium means the same amount changing phase. So I have exactly the same amount of solid turning into gas as I do gas turning into solid if I'm at point B. Okay? There may be a lot more solid than gas at that point, but the exact same number of molecules that are changing phase are the same. Okay? So these are the things that are associated with my phase diagram. Now, there's, of course, exceptions to the rule. This is a slightly different phase diagram. It looks basically the same. It still has solid, liquid, or gas. But let me jump backwards for a second, and you'll notice a difference immediately. Phase diagram 1, phase diagram 2. Did you see it? Let me do it one more time. Phase diagram 1, phase diagram 2. Okay, what did you see? That's right. The solid liquid line in the first one went like this, in more of a straight line. But the solid liquid line over here slopes up and to the left. Really important. Let me explain why. Let's say I was in the solid phase at this particular pressure and temperature, and I raise the pressure of the substance without changing the temperature. Look what happened. as I changed the pressure without changing the temperature, my substance became a liquid. Now wait a second. Think about this logically. What is pressure? Pressure is how compact the molecules are to each other. So if I pack the molecules tighter together, the substance liquefies. Does that make sense? You ever try that before? You ever try and push some things together? Ever turn to a liquid on you? Well, actually, there's one substance that does do that, and you probably noticed it this winter. Ever pack a snowball really, really tight and notice that it kind of gets mushy? Because this is the phase diagram for water. Water is one of those odd substances that when put under pressure, it actually turns from solid to liquid. A phase diagram like this means that the solid is less dense than the liquid. Okay? So, what does that mean? It means solid floats. Hence the reason icebergs. Icebergs form because solid, when it gets compacted into its water, but it gets compacted into its solid phase, turns less dense because the molecules are actually farther apart from each other, even though they're under a higher pressure, okay, or a lower temperature. So again, notice that as I increase the pressure, the substance becomes a liquid. Does this happen often? No, it's very few substances that can do this, but water is the most common, and this will pop up. Again, notice the difference between the two. You can go back and forth in the videos so you can see them. But again, the difference is the line slopes up and to the left, and as you increase the pressure, the substance becomes a liquid, and that's the key. That's everything that has to do with phase diagrams and heating and cooling curves. So hopefully you should be able to identify simple graphs and identify information from those simple graphs.